First off, I want to say thank you for this opportunity to be a part of this. This is amazing work that you guys are doing. Medical physics is a really important part of helping people and helping to heal people. And you are on the ground floor for this in your country. So I encourage you. I'm very proud of you. And I'm very honored that you would allow me to participate in this forum. So today we're gonna take a brief overview of imaging with a focus primarily on planar radiography. As diagnostic physics and imaging in general is just a very, very broad subject, and focusing on one area could probably spark some interest or spark some conversation that I think could go pretty far. So I wanted to start off first with kind of my experience in the field and what my history is as a medical physicist. Got a bachelor's in physics from Xavier University, went on to get a master's in medical physics from the University of Cincinnati. Then I went on to serve in the United States Air Force as a bioenvironmental engineer and a medical physicist, where I got to practice all three areas of medical physics. I achieved my board certification in therapy physics in 2016, and I'm currently working on my diagnostic physics board certification, prayerfully wrap that up in April. I'm also a PhD candidate at the University of Cincinnati, and hopefully I'll be able to accomplish that this summer. Medical physics roles that I've served in the Air Force, I served as a diagnostic, therapy, and nuclear medicine physicist. I've also ventured into the contract physics world as a partner in Precision Physics, Inc. I've also been a chief of physics for the Ann Arbor Veterans Affairs Medical Center in Ann Arbor, Michigan, here in the States. And currently I serve as, unfortunately, the only diagnostic physicist at the University of Cincinnati. I don't present these mile markers in my career to pat myself on the back or to try to impress you. The reason why I show you this is because I think I have a kind of a rare kind of experience within the States of being a multidisciplinary physicist. And because currently the flavor of physicists in the United States is, concentrating and focusing on one area, whether that be therapy medical physics, diagnostic medical physics, or nuclear medicine physics. But I encourage you, as you venture into developing who you are and who you want to be, make your own path. Choose the path that you want to go. And if you're diligent about it, and if you have a strong will, you'll be able to accomplish some pretty amazing things. This picture to the right here is actually time I got to do medical physics in Afghanistan on a deployment. What you're seeing there is an Afghani local and my medical physics team as we went out to go do some medical physics surveys in the war zone. So I've had some great experience by just being open to what I could accomplish. And I encourage you all to view the field in the same way. You might not have the same path as me, but I guarantee if you work hard and persevere, you're gonna get some pretty interesting opportunities. So let's start off with answering the primary question. Why is medical imaging so important? Well, medical imaging exists as a non-invasive means to perform patient diagnosis. The alternative would be doing some invasive measure that could potentially risk harming the patient even further to get the medical answers that the physician needs to give them context to help treat the patient. So medical imaging is very important because it helps us to live by our #1 credo, which is do no harm. And medical imaging is just, it touches every single specialty in the hospital, and it's extremely important. Typically utilizes ionizing radiation, sound waves, or electromagnetic waves to create digital outputs that represent the patient anatomy. And essentially the goal of medical imaging is to digitize and discretize the patient so that we can view them on a computer screen and once again, help the physician gather information to make a complete medical diagnosis, or as close as we can get to a complete. We also have to know that medical imaging in and of itself is really a team approach. There's not one person that's more important than the other. Everybody has a role, and those roles are very important. So the radiologist is the physician team member that's responsible for interpreting the images that come from our image producing devices. The radiological technologists, the MRI technologists, nuclear medicine technologists are the skilled technologists who typically have about a bachelor's degree level of education within the States, who are responsible for image acquisition. And then the medical physicist has broad responsibility and reach as the person responsible for quality assurance, image quality of the image producing devices. So it's a team approach, and medical imaging is very important. Medical physics, imaging medical physics splits into two broad categories: nuclear medicine radiology and diagnostic radiology. So within the nuclear medicine space, nuclear medicine physics belongs to nuclear medicine. And this is essentially the application, particularly of radioactive materials, to imaging and treating cancer. Typically, this type of imaging is more quantitative and physiological, meaning that what we're really trying to image, instead of just anatomy, we're trying to image physiological or metabolic processes. The medical physicist has the responsibility to ensure image quality is optimized, develop different protocols, and by protocols, I mean the different imaging parameters that we engage in to get the appropriate imaging, regulatory compliance, and patient dosimetry. The nuclear medicine modalities that you may be familiar with are planar imaging, single photon emission computed tomography, and positron emission computed tomography. Diagnostic medical physics belongs to diagnostic radiology, and it's essentially the application of radiation to image patients. And this is more of an anatomical style imaging, where if there's a broken bone or something of that sense, it really doesn't follow a physiological or metabolic pathway. The medical physicist's responsibility is to ensure patient dose and image quality are optimized, develop image protocols, and regulatory compliance yet again. Some of the diagnostic imaging modalities that you may be familiar with is computed tomography, magnetic resonance imaging, and these are cross-sectional forms of imaging, meaning you get a 3D data set. Fluoroscopy is essentially real-time radiography. Ultrasound, which utilizes sound to actually image patients, and it's quite ubiquitous around the world. A lot of places have ultrasound. Planar radiography and mammography. And mammography is essentially centered around imaging the breast. So we want to jump into this idea of radiography, but first we kind of got to define like this idea of projection imaging and the fact that it's a two-dimensional image. And essentially you're collecting radiation readings from one angle to form a two-dimensional image. And the typical modalities for this are digital radiography and computer radiography, which we will, once again, this presentation is more so focused on those two areas. And so the image below, the arrows represent a radiation photons that impinge upon the patient and reach the actual detector. This is what is the crux of imaging, at least in radiography, is the differential attenuation of these photons that come from a radiation source that actually reach a detector. So now if we imagine that we turn this first image on its side, what we see here is a patient that has a radiation source in this middle image, then the patient, then a detector. And then what you see to the right of that is the image that will be produced. And the rays that actually reach the detector is what creates the image. And that's what this is trying to display. So we're going to jump into the physics of transmission imaging, because that's what we're really talking about here. And I want to give you some terms to be able to differentiate between nuclear medicine and radiography images. diagnostic radiology imaging. So there's two broad categories of medical imaging: emission imaging and transmission imaging. Emission imaging is, once again, nuclear medicine, in which you're going to inject the patient with some sort of radioactive material. There's a metabolic or physiological process that's followed, and essentially you're measuring the distribution of that radioactive material due to the physiological process. And typically, the radioactive material that's given is some type of metabolic analog. Maybe it's sugar, maybe it's iodine, for the thyroid. But they typically follow some natural pathway within the body. And the significant part about emission imaging is that the patient becomes the source of radiation. And so when we think of emission imaging, we think of the patient emitting radiation photons. Transmission imaging, on the other hand, is a imaging genre where the source is external to the patient. So you have the source, the patient, and then some type of detector. And so once again, this does not have the physiological aspect to it, but it does give you high quality anatomical data that can be used to make a diagnosis. But it's important to recognize that both these imaging genres utilize the differential attenuation of radiation as it traverses the patient anatomy to create contrast in the image. Regardless, this is to say that the physics of the interactions within the body is still the same. So once again, transmission imaging helps us to evaluate anatomy, while emission imaging helps us to evaluate physiology and metabolism. So let's talk about how radiation is produced within the transmission imaging space. We're going to kind of lead ourselves away from emission imaging, because this talk is about more so the CR and DR. So essentially, with transmission imaging, we have a source outside the patient that's directed towards the region of interest that we want to actually image. The photons either get absorbed or penetrate through the patient, making it to the detector. The photons that penetrate through the detector are converted from photons into your actual image. Now, the way these photons are produced is through a process called Bremsstrahlung or breaking radiation. And essentially, a process occurs where we're accelerating electrons to high energies into what's called an anode. And in that anode are atoms that interact with the electric field of the impinging electron, changing its direction. And as that electron changes its direction, it emits a continuum of photon energy. And so this slowing down, this slowing down of this Bremsstrahlung radiation is the crux of radiation production. And what we see to the right here is actually a radiation tube that describes that. So on the, is that a question? Mohammed? I saw a hand go up. I'm not sure if, I guess we hold the questions to the end, I guess.
Yeah, the questions will be sent to the chat box, so send it to you when it's time. Don't worry.
Okay. What we see here to the right is actually a radiation tube, and the construction of this tube, or the primary parts of this tube, is a filament, which is typically a tungsten filament, which we see here. We apply a high current to it, and electrons begin to boil off, right, off of this filament, of this cathode. Across from that cathode, we have this anode material, which is made of tungsten as well. But between the anode and cathode, we place a high voltage, high potential, so we can accelerate the electrons down that axis into the actual anode. And so once again, that process of Bremsstrahlung occurs, creating that continuum of photon energy. But one important aspect about this whole thing is that there's an incredible amount of heat that's produced from these interactions. In fact, most of the interactions or most of the energy is actually dissipated as heat within the actual anode. And so there's a lot of cooling processes that go on to make sure that the anode does not overheat. And you have to watch heating units and watch the temperature of your system to make sure that it does not overheat. Another important aspect of it that's going to contribute to resolution, which we'll get to later in the presentation, is the focal spot size. And the focal spot size is essentially the size of the surface area of the electrons that are actually impinging onto the anode. And so the smaller that is, the more likely, the more heat in a smaller amount of area is going to be produced. So the more cooling actions you have to do to make sure that it doesn't crack or break, or that there's not some issue with that anode. Now, if we go up to the image above that, this image right here describes the photon continuum I was talking about, where we place a 90 kVp voltage across the anode cathode axis. What we can see here in the, what we can see, this is an important point too, what we can see here in the blue line is what's called an unfiltered spectrum. But first, let's even talk about what the axes are. The axes here on the x-axis is the energy of the photon that's created from bremsstrahlung. The y-axis is the relative output. Once again, for that 90 kV kilovoltage potential placed across the anode cathode axis. What we see is that there's a low probability of creating a max energy or a 90 keV photon, but there's a high probability of creating lower energy photons. Unfortunately, these photons don't contribute to the image quality and only contribute to patient dose, because they're going to almost certainly be absorbed before and have a small probability of being of actually making it outside of the patient and contributing to the image. So what we do to combat that, to reduce patient dose, is we filter that beam such that we preferentially attenuate the lower energy photons and create the spectrum that we see in the red, where we've knocked out a significant portion of that low energy region that's not going to contribute to image quality. Another important point about this is that the average energy for your photon beam that comes from bremsstrahlung is 1/3 of the max energy. So, bremsstrahlung is simple and elegant when explained from this level, but can get very, very complex. Radiation tube design and engineering is a very, very complex field, but this is kind of a simplified version of what's going on inside that tube, creating that bremsstrahlung. So here are some of the parameters that impact radiation production. The kilovoltage peak, or KVP, is the max energy of the photon radiation, and once again is the voltage that you place across the anode cathode axis. As you increase KVP, you increase patient dose. You also increase photon penetration, and you therein increase the photons reaching the image receptor. Milliamperage is the quantity of radiation, and essentially it's the amount of current that you're pumping through your filament. And so as you increase your MA, you increase the dose and photons reaching you increase the dose to the patient and the photons reaching the receptor. The way I like to think about the relationship with kilovolt potential and MA is that you should think of this as almost like a boxer, where the kilovoltage peak is how hard the punch is, and the milliamperage is how many punches you're throwing. So this is going to be how many photons actually make it through to the actual receptor. Other parameters is the milliseconds, or the exposure time. As you increase that, and this is the amount of time, essentially beam on time, as you increase the milliseconds, you increase the dose and the photons that reach the receptor. And it's worth noting that typically parameters that increase patient dose increase image quality. So you have to really think about balancing the needs of the needs of imaging, as well as trying to minimize the amount of dose that we give to the patient. So now we're going to jump into some of the photon radiation interactions and attenuation. And there are multiple photon interactions that I didn't go over here. The reason why I chose photoelectric and Compton is because these are the typical or the most likely interactions that will occur within a diagnostic imaging energy range. And so the photoelectric effect, the way we can visualize it is essentially you'll have an incident with the understanding that all matter is made up of atoms, including the human body. And so these photons, an impinging photon is going to, in a photoelectric interaction, will interact with the inner shell electron of an atom, and that photon will be completely absorbed and ionizing that particular atom and also creating a photoelectron. So the energy from that photon is completely absorbed. In a Compton interaction, on the other hand, instead of the energy being completely absorbed, the energy, there's actually a scatter that occurs where the scatter photon escapes with some of its energy, and then there's a electron, a scatter electron, a Compton electron that's created from that as well. Although an ionization still occurs. And what I mean by ionization is that you have a neutral atom, a charged neutral atom that gets an electron removed, and it becomes a net negative charge, a net positive charge, excuse me, because you've just removed an electron. So the probability of these interactions are going to be based off of the Z, or the number of protons that are in the atom that the interaction occurs, as well as the energy. What we see with photoelectric effect is that as we increase Z, we increase the probability of a photoelectric effect event occurring. And as we decrease energy, we also increase the probability of photoelectric occurring. For Compton, there's a little, there's a very weak dependence on Z and on energy. The primary dependence there is going to be electron density. And pair production is important, but it's not important for the energy ranges that we care about here. Primarily, photoelectric and Compton are going to be our primary interactions that we have to worry about. So now the question becomes, what's the relative amount of Compton to photoelectric? And for particular types of tissue, because it's going to vary from tissue to tissue, because tissues have different stoichiometric compositions, different Z's, and so on and so forth. So different effective Z's, I should say, and so on and so forth. What we see from the graph here at the top at the right, we see that bone has a higher probability of photoelectric, which is expected because the Z is higher because of calcium. We see that for soft tissue, although it has a high probability of photoelectric, it's not as high as bone because the Z is not as high. And we see it fade with similar slope for the percent Compton scatter once we get below the 50-50 line. So this portion is really important in understanding how we're going to create our image, because once again, we said in the beginning that what these imaging modalities take advantage of is the differential attenuation of radiation as it traverses the patient. And so this is where you get that differentiation is in the attenuation, the different attenuation properties of your material. So let's take a bulk look. So radiation interactions are probabilistic. So we got to really understand what we're looking at, we got to look at it from a bulk perspective. And so we start to try to define this term attenuation. And essentially, an absorber or a material has an intrinsic attenuation coefficient, meaning in this value mu, meaning the number of photons that will be absorbed by that material per unit path length. And so this value mu is not just going to be based off of just Z, but it's also going to be based off of energy, but it's intrinsic to the material. It's a part of the material's characteristics based off of Z and based off of its density. And so what we see to the image to the right is we see a group of incident photons that is incident upon a slab. And essentially, this is trying to describe what the attenuation coefficient represents, is that you have an incident amount of photons that come through to interact with that slab, but attenuation processes are going to remove a portion of those, photons. And so some of those photons are going to get absorbed in the materials due to Compton and due to photoelectric effect. And so the photons that reach the detector will essentially form your image. Further, we then escalate it by now trying to say we want to have an even thicker slab. So this is, and I didn't go through the full derivation, but this is where we get the our equation here, the exponential attenuation equation, where I equals I naught e to the negative mu x, where I is our transmitted photon beam, I naught is the incident photon beam, and x is the thickness of our material, and mu, once again, is the attenuation coefficient that is intrinsic to whatever material is there. So the image below that, below our equation there, is kind of a representation of how this plays out clinically. You have a radiation source, then you have your patient, and then you have a detector underneath that patient in image A. In image B, it kind of further describes the process by showing the inner anatomy and showing that you have fat, muscle, air, bone, all kinds of tissues that have different attenuation coefficients that are going to attenuate the beam at different levels, but they all are going to sum up to some net attenuation, some I naught being, some amount of photons being removed from an incident photon beam. And so in image C here, that this is the end result of that attenuation. This image where the white portions of the image are indicating a high attenuation area, and the darker parts of the image are indicating a low attenuation area. So this is how this plays out in a clinical, real life setting. How the simplified physics plays out in a clinical way. But it's also worth noting as well the units of linear attenuation coefficient, which are 1 over some unit path length, or one over some unit of length. But it's also noteworthy to know that density does impact attenuation, because the more dense a material is, more targets for that photon beam to interact with. So we normalize or we remove the density dependence by dividing our linear attenuation by the density, and this is known as the mass attenuation coefficient. So let's take a look at some transmission imaging receptors. So this is going to be brief. So transmission imaging, one of the early receptors was film. And film essentially is made of silver halides. But the way we utilized it clinically is we had a cassette that had a intensifying screen, the film, and then and another intensifying screen right below it. And essentially, this is a method of indirectly amplifying, using the intensifying screens, indirectly amplifying the signal that's going to be received by the film, because the intensifying screen converts the high energy photon into low energy photons, a multitude of them that are more efficient with interacting with the film itself. And so essentially the these intensifying screens help to increase our signal because honestly, the probability of interaction with a thin piece of film, even though silver halide has a high Z, is very, very small. And so we use these intensifying screens to once again be able to reduce the amount of dose that we give the patient, because to be able to get that signal up, we're going to have to give more radiation, and it reduces the dose to patient, and it gives you better image quality. So essentially with film, you create a latent image, and then you have to go through a series of chemical processing to be able to get that latent image into the diagnostic image that the radiologist will use to make a clinical assessment. The next genre is computer radiography. And there's still a latent image created with computer radiography through a phosphor. But the process is a little bit different. Essentially, there are valence electrons that, when they interact with a photon, get excited into what's called the conduction band, and they stay there until they get excited out. And so that's your latent image. But instead of using a chemical process, what we do with computed radiography is we use a red laser that rasters across the phosphor with a light guide hooked into it. And essentially, what happens is when you excite when you de-excite the electrons, they emit light. They emit photon light, and the light guide absorbs it, keeping the spatial fidelity along with bringing out the latent image. So this is one of the older technologies, but it's very functional, and it comes in a cassette form. Now with this one, you have to have a big reader that you put the cassette in, and it performs this process of reading the cassette. The next genre is digital radiography. And essentially that comes in two flavors, direct and indirect. In the indirect detection, we go back to this space of having a phosphor that converts the high energy X-ray photon into low energy photons to make it more efficient with interacting with our actual detector. With direct, it converts the photon energy directly into an electronic signal. Now, the special part about digital radiography that's commonly used is that it uses the thin film transistors, and essentially the electronic signal gets sent to these thin film transistors, and they get stored in an electronics piece that's a part of the singular cells of that TFT, thin film transistor array. And then they're read out at, not instantly, but they're read out at the time that at another time. So these are the image receptors that are common in DR and CR, and really film is going away, has gone away. I haven't seen film. In my limited experience, I haven't seen film done. I have still seen computed radiography used here in the States, and I use it for some of my quality assurance testing as a physicist. But what I've seen as the premier technology right now is digital radiography. And so here's some examples of some of the manufacturers. I'm familiar with, all the way at the right, the Fujifilm. Those are the actual CR cassettes. The rest of these are DR. I've had experience with the Konica Minolta, the Aerial DR, the GE. AGFA is a high quality product, and Carestream produces as well. So what about the signal that's actually produced at the radiation receptors? Well, one thing we have to recognize is that it's an analog signal, meaning that it's continuous with time, and we essentially have to convert this into a digital signal. And so the image to the right here, the image to the right indicates what a signal would come in as, from our detector with, so excuse me, let's look at part B of this image. We see a continuous signal here represented by different millivolts. So if we go 20 seconds into our signal, it's 80 millivolts. And so we have to represent that in a language that the computer can understand. We have to digitize it. And so we use a binary system to be able to represent that. So 80 in binary is 0, 1, 0, 1, 0, 1, 0, 0, 0. And once again, this is a language that the computer can understand, but you have to perform this conversion. Now that you've essentially discretized the patient by actually imaging them, now you have to digitize it by performing a analog to digital conversion. And so we should think of images, digital images, as essentially an array of pixel values. And what pixels are the smallest units of an image. And these hold the grayscale information that tell us the lights and darks of our image. And these values are based on the attenuated analog signal that we got from our detector. So the attenuated, so below here, we see that this raw image, once again, has to be, this group of pixel values has to be converted into a digital signal. And once again, it has to be done through an analog to digital conversion. And there are two steps to the analog to digital conversion process. One is sampling, and the second is quantization. Sampling is what you did with your detector. The information you got from your detector, you sampled the patient. The second piece, quantization, is once again that conversion into the binary code space. So the second piece to this is that for these data points, or for the data that we converted digitally, we still have to utilize what's called a lookup table to be able to put that, to be able to indicate the level of brightness that data should have in our actual image display. And so if you look at the top image, the center, the digital lookup table, for if the x-axis would represent the signal that you got at your detector, and the y-axis would represent the level of brightness. And so, for us, if you get a certain pixel value, 248, it corresponds to a certain brightness based off of that digital lookup table. And it's also important here to express the importance of bit depth, which is the largest number that can be stored in a single pixel. So our gray values are going to be defined by if our pixel is 8-bit depth or 16-bit depth pixel, which means that it has 2 to the 8th shades of gray that can be utilized to describe that image, and essentially is as a value on your lookup table. Another important aspect is that there are even further corrections that need to occur to be able to get the image to be able to be clinically usable. One of the first things, one of the things that you have to do to the raw data is you have to perform different corrections. Defective pixels, pixels that are blacked out, you have to correct for that. Non-uniformity in pixel response to the same stimuli, you have to correct for that. Corrections in the fact that the gain across the imager may not be uniform. and also geometric distortions. And then there's a second set of corrections that you have to do that are specific to the volume or region of interest that you care about. In histogram equalization and edge restoration and noise reduction. So these are it's not just as simple as taking an image. There's a lot of secondary kind of corrections that have to occur to be able to get the image clinical. So let's jump into image quality. So image quality is essentially how accurate your image reflects what's occurring in reality. So an example would be with your phone. If you took a picture, how well does that picture really show what you took a picture of? And there are two main parameters that we evaluate image quality off of: spatial resolution and contrast resolution. So in spatial resolution, we think of this as the image sharpness, and increasing spatial resolution makes the image clearer and allows for better visualization of fine detail. Essentially, the number of pixels that are in your image are going to be what's going to define how much resolution you have in your image. To be able to measure this, we utilize, and on the next slide we'll get into a little deeper, line pair phantoms to be able to evaluate what our resolution is. There are way more complex methods for evaluating resolution, such as the modulation transfer function, edge functions, all these complex mathematical tests that you could perform. But in the field, typically we use bar pair phantoms because they're simple. They allow us to baseline and have constancy of our tests across, very easily. And they're reliable and they're easy. And it gives me a sense of whether or not there's an issue with my resolution in a very, very simple manner. The things that impact spatial resolution is pixel size, number of pixels per image, and the focal spot size, as we spoke of before. So in the image below of Idris Elba, we see the image all the way to the right, the blurry one, is 480 by 480 pixels, which means it's a very large pixel and it's very few. But you see, as you go left, the clarity in the edges get more and more clear, and you're able to see Idris Elba very well. How does that play out clinically? If we look up to the right here, we see a radiograph of a chest. We see a radiograph of a chest, and we see that the high levels of pixelation for very large, very few pixels going from D to A. And once again, we measure resolution via a bar pair phantom. With regard to contrast is the ability to distinguish varying shades of color. And since medical imaging is composed of grayscale contrast, it's a measure of essentially the shades of gray. The better the contrast, the easier it is to distinguish between two different tissues. And once again, what impacts contrast? Bit depth, the energy for which you image, as well as the MA and the mass that you image with. And once again, the way we measure this in the field is typically some type of contrast detail curve, where you have a phantom that has some holes drilled in it of varying thicknesses and varying sizes, and you want to basically determine which holes you can see on a consistent basis. So if there are any questions, please don't be afraid to email me. I'll leave this via Busa to hand out. There's definitely more depth that we can go into each of these subjects, and I would be more than happy to give that to you. Also, before I got out, I would be remiss to not mention this. It's African American History Month, Black History Month here in the States. And here are some of the major contributors to radiology within our field. I'll just mention a few to give you guys the knowledge. Marcus Wheatland, MD, was the first African American radiologist in the United States. The first African-American medical physicist to be board certified by the ABR is Dr. Louis B. Levy, and the first African-American radiological technologist was Miss Rose Perkins. And so there's a whole compendium of history of African-Americans' contributions to radiology and radiation sciences that's out there. If you want to talk about that, please don't be afraid to email me either. Thank you for your time. I appreciate participating, and I am done.